Hello there, and welcome to Sleepy Cosmic Podcast, where quiet curiosity meets the night and wonder is allowed to take its time. Above us, far above the turning of our planet and the shimmer of city lights, something ancient is drifting in from between the stars, a soft traveller, a body of ice and dust, silent and alone, not from our sun's gentle family but from somewhere else entirely, out there, past the distant arms of the Milky Way. It's called 3i Atlas, a name that feels almost too small for what it represents. The 3i means it's the third known interstellar object we've ever spotted, just 3, in all our history of watching the sky. As we settle into tonight's story, we won't chase headlines or worry ourselves with big alarms. Instead, we'll breathe slowly and let the presence of 3i Atlas unfold, like a quiet ripple across a calm pond. We'll listen to the whispers of its orbit, the chemistry of its tail, the instruments that found it, and the gentle scientific wonder that surrounds it. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. And if you'd like, take a moment to notice where you are. The feel of the pillow beneath you, the way the air moves in your room, the local time wherever you are in the world. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin with the simple fact: 3i Atlas is not from here. It doesn't loop our sun like Mercury or trail our orbit like the Trojan asteroids. Its path is different, so different in fact that it couldn't have started in our solar system at all. Its orbit is hyperbolic, which is a quiet way of saying this object is passing through. It arrived from the outside and soon enough it will be gone again. That one detail is what makes this moment so rare. Most comets loop endlessly around the sun in elongated ellipses, bound by gravity. But this one, it's unbound. Its speed, its angle, its arc through the sky, all point to a story that began light years away. What's fascinating is how ordinary it looks at first glance. Just another fuzzy dot against the velvet sky, with a soft coma and tail like other comets we've catalogued. But when astronomers looked closer, ran the math on its movement, they realised it wasn't looping. It was gliding. It was escaping. And yet, for all its foreign origin, it's not moving impossibly fast, not screaming through the solar system. In fact, it's moving just a little above solar escape velocity, just enough to be free. That small excess speed is a key signature of interstellar objects. The first one we found was Oumuamua in 2017, then Borisov in 2019. Now, 3i Atlas joins their quiet ranks, and as with the others, its arrival brings more than data. It brings perspective, a whisper from another star system wrapped in ice and dust. We can't know exactly where it came from. Maybe a sun like ours, maybe a red dwarf or binary system, maybe a quiet ejection during planetary formation, long before Earth was even a dream. Its surface chemistry may hold hints. The gases it releases might match or differ from our familiar comets. But nothing will offer a full return address. There's something poetic in that, an unmarked envelope drifting in from deep space. We open it gently with telescopes and spectrometers, try to read what we can before it fades away again, and fade it will. By early 2026, it will have passed the Sun, past Jupiter, and slipped back into the dark, a guess that never really stopped to stay. But for now, we have it, a moment of contact, a whisper across space, and as we breathe and drift deeper into the night, we'll follow that whisper, one gentle chapter at a time. Why interstellar visitors matter? We reflect on why these rare wanderers spark both awe and caution. It's easy sometimes to think of our solar system as a kind of island, a self-contained place with well-behaved planets, looping moons, and the occasional comet spiralling in from the outskirts. But every so often something crosses the border, something that didn't start here, something that reminds us we're not alone in space. 3i Atlas is one of those reminders, a soft signal from beyond our neighbourhood, and it's not just its origin that catches our attention, it's what it represents. When we see something like this glide through our sky, we're witnessing more than a lone comet. We're glimpsing the long, slow drift of the galaxy itself, because for every 3i Atlas we detect, there could be thousands more passing silently between the stars, most too dim, too small, or too distant to notice. These visitors matter because they break the pattern. They break it gently, yes, but meaningfully. For all our models and simulations, we still have gaps. The early solar system, planet formation, the migration of dust and gas in proto-disks. Interstellar objects offer rare physical clues, solid particles from other star systems. A taste of alien chemistry, a chance to test what we only guessed before. And there's also a deeper question hiding inside each interstellar object. Why now? Why did this fragment arrive here, now, while we're watching? Not in a magical sense, just in the quietly astonishing realization that, out of the billions of years and trillions of kilometers it could have travelled, its path intersected with ours. This one, solitary object, wandering for perhaps 1 billion years, now glows faintly in our telescopes for a handful of months. It's a beautiful alignment. Still, we also know this: interstellar objects are fast, and their windows are brief. That's part of why they stir both awe and a kind of nervous energy among scientists. We have only so much time to observe, only so much data we can gather before they're gone again. And with 3i Atlas, there's a small edge of worry beneath the wonder. Not because it threatens us, there's no sign of that, but because it's different enough and large enough that we don't want to miss what it can teach us. Some models suggest it's much bigger than the previous 2 interstellar objects, perhaps as large as 10 or 11 kilometers across. That alone makes it special, large enough to survive heating from the sun. Large enough to outgas steadily, showing us more of what lies beneath its crust. More data, more time, more chances to wonder. And with each observation, we slowly peel back layers of possibility. Could it be a fragment from a planetary collision in another system? Could it be carrying carbon-rich molecules that formed before our sun ignited? Could the ratio of volatile gases hint at colder or hotter birthplaces? We don't know yet, but this is how science moves, softly, patiently, with eyes wide open and instruments tuned to the dark. There's also something comforting in that process, in the way we turn curiosity into method. In how we build instruments like Rubin, Hubble and JWST not just to stare into known spaces, but to stay ready for the unknown. Because the truth is, we were never expecting 3i Atlas, just like we weren't expecting Oumuamua or Borisov. Each one of these travellers was a surprise, a reminder that the universe isn't a closed book, it's still writing itself. And as we float quietly here, beneath this pale sky, we can appreciate the humility that takes. We don't command the cosmos, we listen, we wait, we observe. Sometimes, in the quiet of night, that's enough. We follow its path next, not just in space, but in shape. You see, the way something moves tells us something fundamental about where it comes from. And for 3i Atlas, its trajectory speaks in quiet certainty. It is not from here. When astronomers plot the motion of objects in the solar system, they usually find ellipses, loops, bound orbits that curve around the sun and return again. But 3i Atlas doesn't loop. It arcs. A soft curve, open-ended, a hyperbola. That's a word with precision behind it, hyperbolic orbit. It means this object is on a one-time pass. It's not part of the sun's gravitational family. It's not coming back. It moves too fast, too straight, too free. Its eccentricity, an astronomical measure of how stretched an orbit is, exceeds 1. That's the giveaway. Anything above 1 is unbound. and 3i Atlas clears that threshold with quiet confidence. Of course, these aren't things we can see with our eyes. If you were to look up and spot it through a telescope, you'd just see a faint glow, a small fuzzy point with a tail. But behind that glow lies velocity, tens of kilometers per second. It's already accelerating away from the pull of our sun, even before it reaches the closest point in its journey. This escape arc is what first tipped astronomers off. Before anyone knew its chemical makeup or exact size, its path was already whispering, "I come from elsewhere." What's remarkable is how consistent this story is with past visitors. Oumuamua had a similarly steep curve, though it arrived more like a skipping stone, with almost no outgassing, no tail. Borisov II behaved more like a textbook comet, and now 3 Atlas III brings its own version. It brightens as it warms, just like Borisov, but its arc is steeper, its curve more extreme. All three remind us that our solar system, vast as it seems, is porous, not sealed, not a bubble. From time to time, the space between stars sends something through, and it's not just the shape of the orbit that matters, it's the direction. Most solar system objects lie close to the plane of the ecliptic, the flat, gentle disk where the planets orbit. But 3i Atlas cuts across at a sharper angle, an outsider's trajectory, one that hasn't been shaped by billions of years orbiting the sun. Its journey began far away, maybe in the scattered edge of another solar system, maybe from the collapse of a cloud that never formed planets. Perhaps it drifted for eons before brushing too close to a star or gas giant, slingshotted outward, and sent flying through interstellar space. It's hard to overstate just how long a journey that would be. Tens of thousands of years, hundreds of millions, possibly longer. There's no precise timestamp on when it was ejected. Only its velocity gives us a hint, a long, slow voyage through the dark. And now, for just a handful of months, it enters the sunlit stage of our sky. It passes no judgment. It asks for no attention. But we notice it, and we track it. Because each time one of these visitors arrives, it changes the edges of our maps. Some of the earlier simulations showed that 3i Atlas will reach perihelion, the point closest to the Sun, around late October 2025. But already its trajectory is clear. It's not slowing enough to fall into orbit. It's not looping around. Its line will bend gently past the Sun, curve out toward the orbit of Jupiter, and keep going. Even that curve is shaped by other hands. The gravity of planets, especially Jupiter, nudges the path, just slightly, as if the solar system gives a soft bow, then lets go. There's something humbling in that. This object was never ours to hold. Not even the Sun, with all its gravity and brilliance, can keep it. And so we mark its path, not with claim, but with quiet admiration. We map the gentle arc, the fading line it will draw as it slips away. You might imagine it like a brushstroke on a vast canvas, painted slowly over millions of years, visible to us only for a blink. But it leaves something behind, not debris, not danger, just a subtle expansion in what we know is possible. It reminds us that orbits don't always close, and journeys don't always return. Some things pass through, touch us briefly, then move on. And as we drift further into the night, we carry that thought with us, soft and open-ended, like the path of 3i Atlas. We drift now toward the core, the nucleus of this traveller. It's a distant thing, small and shrouded in its own vapour, yet it holds the heart of the mystery. Beneath its growing coma, that hazy glow of gas and dust, lies something solid, something ancient. But how large is it really? That question, surprisingly, remains open. Not because we're uncertain in general, but because measuring the size of a distant active comet is harder than it seems. We can't just point a telescope and take a cosmic ruler to it. The coma, those particles escaping from the surface, obscures our view. It reflects sunlight and masks the shape of what's underneath. Even so, observatories have tried. The Hubble Space Telescope offered early estimates, suggesting a size somewhere between 320 metres and 5.6 kilometres across. That's a wide range. Somewhere between a hill and a small mountain. Large enough to matter, small enough to hide in the glare of its own reflection. But later, the Vera C. Rubin Observatory, designed to track faint moving objects in the night, captured data that suggests something more substantial, maybe 10 kilometres, maybe 11. That would make 3-Eye Atlas larger than either Oumuamua or Borisov, possibly by a factor of 5. We might imagine a dark, icy body roughly the size of Mount Everest, coasting quietly through space, covered in frozen carbon dioxide laced with silicate dust, layered with the chemical memory of another star's nebula. Still, it's not just about size. What matters is how that mass behaves, how it breathes, how it warms, how it sheds. The nucleus may be compact, but it's alive with energy, in its own quiet way. As it nears the sun, surface ices sublimate, transform directly from solid to gas, forming jets that stream outward and create the tail we see. And those jets aren't random. They're shaped by the spin of the object, the location of sunlight, and the texture of the surface. From millions of kilometers away, we can't see the terrain directly, but we can infer its story through the outgassing patterns. They create little asymmetries in brightness, little lopsided trails of dust, and from that, we begin to sketch its silhouette. It might be round, or it might be elongated, like a shard of something older. We don't know yet, but its activity gives us clues, and those clues hint at a nucleus that's not just cold and silent, but dynamic in motion, responding to light, responding to time. There's also a softer mystery. Why is it still active? Comets that have travelled the solar system for billions of years often run out of surface volatiles. They grow crusted over, quiet, dark. But 3 Atlas, coming from interstellar space, is still fresh. Its ices are likely pristine, untouched by solar winds, untouched by the warming pulses of repeated orbits. That freshness matters. It means what we see is close to its original form, perhaps unchanged since it first condensed in a cloud of dust and hydrogen light years away. And so we study its glow. We compare the rate of sublimation to the light we see. We estimate how much material it's losing, and from that, how big the nucleus must be to survive its brief time near the sun. What we find is a comet large enough to remain intact, but not so massive that it draws undue gravity, just big enough to be noticed, just bright enough to whisper. Of course, models vary. Astronomers still debate the reflectivity, the albedo, of the coma. A darker nucleus reflects less light, so it would need to be larger to explain what we see. A lighter one, brighter with surface frost, could be smaller. And then there's the question of shape. Round objects reflect differently than irregular ones. It's a science of patience, of gentle margins and long exposures, of gathering photons from something so far away it barely moves in the sky. Yet even now, 3C Atlas teaches us to be humble. We don't know everything, not yet. We make careful guesses. We revise. We compare against the quiet archives of other comets, other fragments, and we wait. Because with each observation, we add a piece to the picture. A picture of an object from another world, drifting silently through ours. And as we drift with it, letting the numbers and shapes settle into the background, we're left with a simple image, a nucleus, dark and ancient, wrapped in a breathing veil of gas, trailing a tail of stardust behind it. A traveller with no voice but motion, no light of its own, only what it reflects, and yet it speaks, if we're still enough to listen. The coma, that faint and glowing cloud around the nucleus, tells a quiet chemical story. As 3-Eye Atlas moves closer to the sun, the warmth begins to coax out gases that have been frozen solid for perhaps billions of years. It's a gentle awakening, and each molecule that escapes carries with it a fragment of memory from wherever this object began. Among the first to be detected is carbon dioxide, CO2, streaming out into space in invisible jets. It's a familiar gas, one we know well on Earth, and yet here, in the cold vastness of interstellar space, it becomes something more, a messenger from another system. Alongside it, we find water vapour, carbon monoxide, cyanide, and faint traces of atomic nickel, each one a quiet clue to the conditions under which 3I Atlas formed. Water and carbon monoxide are common in comets from our solar system, but cyanide? That's especially interesting. On Earth, it's toxic. In space, it's a building block, one of the raw ingredients that, over eons, might participate in the chemistry of life. And in interstellar comets like this, its presence could suggest that the material drifting between stars is rich, not barren. What makes this even more beautiful is that we don't see these molecules directly. Instead, we detect their light, or more precisely, the way they absorb and emit certain wavelengths. Instruments like NASA's SphereX mission are built for just this kind of work, collecting spectral fingerprints that tell us, gently and precisely, what these far-off bodies are made of, and each fingerprint adds to a quiet archive. One more point of data suggesting that the chemistry of the galaxy isn't uniform, but it's not chaotic either. There are patterns, there are echoes, and sometimes, like now, those echoes reach us in the form of a glowing tail in the night sky. The tail itself is changing already. Early observations from the Gemini South Telescope revealed its birth, barely visible. A faint brushstroke in the dark. Then, as the weeks passed, the tail grew. Longer, brighter, carried by solar wind and shaped by the particle flow of the sun. It arcs gently behind the nucleus, always trailing away from the light, like a shadow made of starlight. That tail doesn't just glow, it speaks. The shape and density of the particles tell us how fast the gas is leaving the surface, whether it's being released in steady jets or in sudden outbursts, whether the dust is fine and slow or coarse and quick. And slowly we build a map, not of geography but of activity. Some comets shed their material in unpredictable bursts. Others, like 3I Atlas so far, appear to exhale in a steadier rhythm. A long, quiet release, as though it's been waiting for this moment of warmth for a very long time. What's especially fascinating is that, despite its interstellar origin, much of its chemistry so far resembles what we've seen in comets closer to home. That's unexpected. We might have imagined something alien, strange molecules, unfamiliar volatiles, but instead we find cousins. Distant, yes, but related. It suggests something gently profound. The processes that form icy bodies around stars might be common. That out there, beyond our reach, other planetary systems are forming with the same basic ingredients. That across the galaxy, chemistry repeats itself, in different places, under different stars. Still, it's not a perfect match. There are subtle differences, slight shifts in ratios, perhaps a bit more carbon monoxide than usual, perhaps the presence of elements not yet fully measured, and these differences keep the mystery alive. Astrophysicists still debate what they mean. Is 3I Atlas truly pristine, unchanged since its formation? Or has it been altered along the way, heated by a passing star, impacted by another object, reshaped by time? We don't know yet. And maybe we won't, but the debate itself keeps our questions sharp. It's also possible that some of these molecules predate the comet itself, that the dust and ice within 3 Atlas carry echoes from the molecular cloud where it formed, a place where hydrogen and helium mingled with carbon and oxygen in the cold, quiet dark. If so, this comet isn't just a relic of another solar system, it's a remnant of galactic history, a preserved piece of chemistry that saw the galaxy in its younger days, and now, as it drifts past our sun, it releases those molecules into our space, into our instruments, into our understanding. It's easy to overlook that kind of beauty, the way deep time and deep space converge in a single point of light. But as we breathe here, slowly and softly, we can let it settle in. Three-Eye Atlas may never visit again, but for this brief season it shares its breath with us. We turn now to memory, not our own, but the memory held by this quiet traveller's predecessors. Three-Eye Atlas is not the first of its kind. Two others have passed before it, each offering their own silent testimony from deep space. Together, they form a kind of trilogy. A soft unfolding of cosmic visitors, rare and brief, yet each one distinct. The first was Oumuamua. Detected in October of 2017, it was the one that truly opened our eyes. No one expected it. It appeared suddenly in the data. A fast-moving object with a strange, cigar-like shape and no clear comet tail. It didn't behave like anything we'd seen before. It reflected light oddly, spun irregularly, and changed speed in a way that puzzled even seasoned astronomers. Oumuamua stirred debate. Was it a comet without a visible coma? A shard from an interstellar collision? Or something else entirely? Some even wondered aloud if it might be artificial, a kind of probe or fragment from a distant intelligence. But in the end, the consensus leaned toward a natural object, even if its details remain, to this day, softly unsolved. Then came Borisov. In 2019, we saw what looked more familiar. A comet with a bright coma, a long tail, and a chemical fingerprint similar to the comets of our own system. But it too came from beyond. Its orbit was hyperbolic, its path unbound. It confirmed what Oumuamua only hinted, that our solar system is not a closed shell, that other stars too send pieces outward, and now Three-Eye Atlas, the third visitor, perhaps the most revealing so far. Compared to Oumuamua, Three-Eye Atlas shows much more classic cometary behaviour. A visible tail, an active coma, molecules we can measure. Where Oumuamua was all mystery and absence, Three-Eye Atlas gives us presence, substance, data, light. In a way, it's like stepping into a dream where each layer becomes clearer, not more blurred. And compared to Borisov, Three-Eye Atlas is larger, perhaps older. Perhaps from a colder region, judging by its abundance of volatiles. It may carry even more pristine material, less processed, less altered by time and heat. Still, each of these objects brings its own questions. Oumuamua made us reconsider what a comet even is. Borisov confirmed that interstellar comets can resemble our own, and Three-Eye Atlas now stretches our models, its unusual polarization, its size, its activity, all nudge at the edges of what we thought we knew. Together they whisper a shared message. We are part of a much larger system, one where fragments cross the space between stars more often than we realized. One where interstellar travel doesn't require a ship, just a gentle push and enough time. It's tempting to ask, how many others have passed through, unseen? How many interstellar objects have skimmed past our sun before we had the instruments to notice? The answer is probably many. Most would be too small, too dark, too fast to detect. But they were there, sliding through the solar system like quiet shadows. Now that we've seen 3 in less than a decade, our perspective is shifting. Some astronomers estimate that there may be millions of interstellar objects drifting through the Milky Way at any given moment, not in a swarm, but in a diffuse, slow-moving ocean of fragments, each one a story from elsewhere. And some of those stories end here, or at least pass through. There's a kind of continuity in that, a cosmic rhythm. One object arrives, then fades. Another appears. Slowly we build a vocabulary, a soft lexicon of visitors, and with each one we become a little more fluent in the language of deep space. Of course, all this observing takes patience. Years of ski surveys, teams of scientists passing through faint smudges of light, algorithms trained to spot movement against the starfield, instruments finely tuned to detect the quietest breath of a comet tail. It's not glamorous work, but it's beautiful, because each detection, each light curve, each orbital calculation brings us one step closer to understanding how the universe shares itself with us. Oumuamua, Borisov, Atlas. 3 names, 3 objects, 3 quiet steps toward the realization that our corner of space is not sealed. It's a window, and sometimes the wind outside carries visitors, so we wait, we watch, and we wonder what the next one will bring. The journey of 3-Eye Atlas through our gaze has not gone unnoticed. Some of the most detailed early detections came from a telescope designed for just such things, the Vera C. Rubin Observatory. Still under construction for much of the last decade, Rubin's wide-field design is tailored to scan the night sky with remarkable speed and resolution. Its camera, the largest ever built for astronomy, is capable of capturing broad swaths of space in a single exposure, catching transient objects that might otherwise slip by in the dark. It was with this calm vigilance that Rubin captured 3-Eye Atlas, quietly cataloguing its slow drift through the heavens. These first images weren't dramatic. They were subtle, a shifting point of light across sequential nights, moving against the background stars with a grace only computers could track. But within that motion was the signal, a hyperbolic arc, not bound by solar gravity. What made Rubin's observations so vital wasn't just that it saw the object, but that it saw it early. With interstellar visitors, time is precious. The sooner we detect them, the more we can learn. A few extra weeks of sunlight on the comet's surface can yield dramatic changes in activity. A little more time means better models, deeper insights, and clearer spectra. Rubin's data suggested something large. The brightness, even from far away, implied that this was not a small shard, but a more substantial body, something that would likely survive its pass through the inner solar system without breaking apart. That alone was exciting. We'd seen Oumuamua's odd behaviour, watched Borisov's long tail, but now we were looking at a third object, possibly more pristine, certainly more massive. But Rubin doesn't see alone. Across the globe and above the atmosphere, other instruments quickly joined in. Hubble, ALMA, even small robotic observatories began tracking the faint arc of 3-Eye Atlas across the sky. But it was Rubin's ability to capture broad, sweeping images night after night that let us place this traveller into context. From those images, we gathered clues, not just about the nucleus, but about its interaction with solar light. We watched the coma form and expand. We measured the outgassing. We watched the tail begin to stretch. All of it unfolded like a slow breath, and through it we learned. The observatory's contribution isn't just in the moment of discovery, but in the way it creates continuity. By capturing full-sky surveys over and over again, Rubin helps us build a memory of the night sky. When something changes, when a new light appears, or an old one shifts, we know. And we can look back through those records to find the earliest traces. That's what happened here. After the first detection, astronomers combed through Rubin's archive to find the comet in earlier images. Precovery, they call it. Looking back to find what was already there. And each recovered image pushed our understanding further, refining the orbit, adjusting the velocity, sharpening our knowledge. It's a quiet kind of detective work, one that involves no rushing, no urgency, just the slow layering of detail upon detail until a picture emerges. Even as the object brightened, Rubin continued to observe. It measured the tail's lengthening. It charted the coma's changing symmetry. And as the comet drew closer, Rubin's images became a kind of journal, each one a new page in a story unfolding between stars. There's something poetic about that. This observatory, built to scan the night with automated precision, ended up offering something soft and human, the gift of time. Not in hours or days, but in awareness. It let us see the visitor sooner, let us follow it longer, Let us ask better questions before the answers fade into the dark again, because that's the truth of these moments. They are brief. Even now, the clock is ticking. By the end of 2025, 3i Atlas will already be fading. By mid-2026, it may be gone from view entirely. Just one more moving light in a sea of darkness, but thanks to Rubin, we'll remember. We'll have the record, not just numbers but images, light curves, spectra, all the quiet traces of a visitors we could not keep, and maybe, just maybe, we'll be ready a little sooner next time. Hubble, that aging sentinel orbiting above our world, also turned its gaze toward 3i Atlas. Where Rubin scans wide and often, Hubble looks deep. It sees in exquisite detail, collecting ancient light with the patience of a quiet observer who never sleeps. And when it focused on this new interstellar visitor, it added something intimate to the story: scale, motion, and texture, drawn from thousands of kilometers away. Hubble's early measurements were aimed at estimating the nucleus size. Unlike the wide-field images from ground-based telescopes, Hubble could resolve subtle shifts in brightness within the coma, those delicate gradients of light that hint at what lies beneath. By analysing those patterns and comparing them to models, astronomers inferred a range for the object's size. The numbers came with wide margins, anywhere from 1/3 of a kilometre to more than 5. But even those uncertain figures told us something important. This wasn't a tiny shard. It was large enough to hold on to its volatiles, large enough to be active, large enough to be seen with clarity. And as Hubble watched over the days and weeks, it did more than measure. It tracked behaviour. The way the coma grew. The way the light shifted, the subtle changes in brightness as sunlight fell at different angles. From this, scientists could infer rotational properties, even hints of shape. One curious feature emerged. The activity appeared smooth, not erratic. No dramatic outbursts, no sudden fragmentation, just a steady release. That too told a story. Comets that have been battered or spun too fast often crack and splinter under solar stress. But 3i Atlas so far was holding together. A quiet strength, a kind of resilience born from ages of isolation. Hubble also helped isolate the spectrum of light coming off the coma. Those signatures revealed the presence of carbon-bearing molecules, oxygen-bearing compounds, and some rarer elements like nickel. Not just the basics, but the subtleties, ratios and combinations that hint at the conditions under which the comet formed. Nickel, for example, doesn't sublimate easily. Its presence means temperatures inside the comet are higher than expected, or perhaps that fine nickel dust is being lifted by escaping gases. Either way, it points to complex chemistry. And then there's cyanide. Detected faintly in the light, it's both familiar and otherworldly. In comets, it's often found as CN radicals, fragments of longer carbon-nitrogen chains that were broken apart by sunlight. And while we think of cyanide as dangerous here on Earth, out in space, it's part of the basic chemical grammar of carbon chemistry. It reminds us that the ingredients of life, simple, dangerous, beautiful, exist all over the cosmos. Still, there's much we don't know. Hubble sees with precision, but even it cannot resolve the nucleus directly. All we can see is what escapes, what shines. The object itself remains a silhouette, hidden in its own breath. That mystery fuels the debate. Could this object be unusually dark, highly reflective, covered in fresh frost or layered with carbon dust? The coma's brightness gives us clues, but no final answer. Astronomers have floated multiple models. Some suggest a dark, tar-like surface, absorbing most of the sunlight. Others imagine a more reflective coating of water ice. Still others propose layered strata built from slow accretion in the outer disk of a now distant star. And Hubble, steady and patient, continues to watch. Even now it collects data on the tail structure, the coma's thickness, and the way particles scatter light. From this, we'll eventually build a more complete picture, not perfect, but full of meaning. One reason Hubble's perspective is so valuable is its distance. High above Earth's atmosphere, it sees without distortion. No twinkling, no blurring, no weather to wait out. It just stares, in silence, as light from across the void arrives. And it doesn't just look at Three-Eye Atlas, it compares, it catalogues, it connects what it sees now to what it's seen before. Borisov, Oumuamua, countless long-period comets. In doing so, it helps us map where this object fits in the wider tapestry. Already, the patterns are intriguing. Some aspects of Three-Eye Atlas resemble Oort cloud comets, long-period wanderers from the far edge of our solar system. Others match traits seen in newly formed comets from exoplanet simulations. It's as if this one object sits quietly at the crossroads of several stories. Hubble helps us listen to those stories, and so we return gently to the image. A distant body, ancient and unknowable, cloaked in its own light, drifting through our system with slow confidence, seen by human eyes only because we built instruments steady enough to catch it. A traveller noticed, measured, admired, and in that noticing, we grow. We drift now into deeper time, guided by a question that lingers like starlight long after its source fades. How old is Three-Eye Atlas? It's not an easy question to answer. We can't carbon date a comet from afar. We can't drill into its layers or touch its frozen skin. But we can listen to the quiet clues it offers. Its orbit, its chemistry, the way it responds to sunlight. And from that, we can make a gentle guess. Many astronomers believe this object may be astonishingly old, perhaps older than the Sun, maybe even older than the solar system itself. That possibility opens a vast mental horizon. Imagine an object formed in the cradle of another star, born in a collapsing cloud of gas and dust before Earth was more than a cloud of particles. Imagine it orbiting quietly for hundreds of millions of years, maybe even billions, around a star we'll never see, in a system we'll never visit. And then, nudged by some distant event, a passing star, a gravitational tremor, it begins to drift outward, not toward us, just away. It might have floated in the space between stars for longer than all of human history, untouched by heat or light, until it finally crossed paths with our solar system in 2025. That journey, longer than memory, deeper than language, is part of what makes this moment so quietly profound. When we speak of ancient things, we often mean ruins, rocks, fossils. But this is ancient in a cosmic sense. Not millions of years, but billions. Not shaped by human hands, but by the cold architecture of gravity and time. And perhaps within that ice lies chemistry even older. Molecules that formed in the interstellar medium before Three-Eye Atlas was born. Before its parent star ignited. Before the spiral arms of the Milky Way spun into their current shape. In this way, the comet is a kind of time capsule, not sealed deliberately, but preserved by chance and distance. It holds within it not a message, but a memory, a physical memory of conditions that no longer exist in a place we can't name. And still, we wonder. How common are such ancient wanderers? How many fragments of long-lost systems drift through interstellar space, never seen, never known? If we had better eyes, stronger telescopes, more sensitive detectors, would we see them everywhere? Or is this rare? A quiet coincidence that, among all possible paths, this one comet happened to enter our skies. The truth is, we don't know, but instruments like the Vera C. Rubin Observatory may help us find more. We're entering a time when wide sky surveys are becoming frequent enough, precise enough, to catch these faint visitors earlier, and with each one we learn more about what lies beyond our solar system's edge. Yet there's another more humbling layer to the question of age. Some studies suggest that Three-Eye Atlas may come from the Milky Way's thick disk, a population of stars and objects that are generally older, slower, and less chemically enriched than those in the thinner disk where our Sun resides. If that's true, then this object could have been travelling since the galaxy was young. Perhaps even since shortly after the first generations of stars exploded and seeded space, with the heavier elements needed to form solid bodies. And so, while we often think of comets as cold and quiet, this one may be carrying the echo of supernova, the remnants of long-dead stars folded into grains of dust and frozen in ice, waiting for starlight to set them free again. This is part of what makes astronomy a kind of quiet poetry. We look into the night and see not just space but time, not just distance but history, and with each passing object we add a verse to the story. 3i Atlas, for all its silence, speaks that verse well. It tells us that the galaxy is older than we can hold in our minds, that its stories are not told in words but in movement, in chemistry, in light, that even the smallest object, just a few kilometers across, can carry the weight of deep time. And as we watch it arc across the sky, backlit by the same sun that warms our skin, we can let that time settle over us. Not as fear, not as mystery, but as perspective. Because if this object truly is billions of years old, if it has travelled farther than any probe we've ever launched and seen more nights than all of humanity combined, then its quiet passage through our system is a kind of gift. Not a warning, not a threat, just a soft reminder that the universe is wide and we are part of it. We stay with this idea of movement, slow, patient, ancient, and shift our gaze to the question of how an object like 3i Atlas ends up on such a path at all. How does something become interstellar? What sends it out from its birthplace and into the quiet void between stars? There's no single answer, but the galaxy offers several gentle mechanisms, possibilities that, over time, guide small bodies like this one away from their home systems. One of the most common is gravitational scattering. In the early days of a planetary system, things are not yet settled. Planets are still forming, often migrating inward or outward, sweeping up material as they go. In that era of motion and chaos, a comet or asteroid might find itself in the wrong place at the wrong time. A close pass with a gas giant, a massive planet forming near the outer edge, can fling a small body outward, not just into a long orbit but into escape. The energy transfer sends the object beyond the gravitational reach of its star, and from there it drifts, unmoored, unbound. It could take thousands of years to fully leave the system, but eventually it does, and once free, it becomes a kind of ghost, moving through space with no central body to orbit, no warmth, no anchor. Another possibility: passing stars. In the vastness of the galaxy, stars do occasionally approach one another, not in collisions but in near brushes. When they do, their combined gravitational fields tug at the outermost debris around them. If a comet lies on the edge of its system, that passing star can alter its path just enough to send it outward. Even binary stars, two stars orbiting one another, can eject material during their evolution. The dance of their gravity can pull small objects into complex paths, some of which spiral outward and never return. There's also the matter of planetary disruption. If a system experiences major instability, perhaps a planet gets ejected or swallowed by its star, the delicate balance of orbits can shift. Some objects are thrown inward, others outward. A few may become interstellar travellers. What all these processes share is time. They happen slowly, over millions of years. There's no explosion, no drama, just gravity nudging and shaping, one orbit at a time, and eventually an object like 3i Atlas is no longer a member of its birth system. It's a traveller, alone, but not lost. We can't know which of these paths this comet followed. Maybe it was ejected by a forming planet. Maybe a distant stellar neighbour nudged it just slightly. Maybe it was part of a system that no longer exists, a remnant of a star that collapsed or flared away. That uncertainty is part of its poetry. We know so much about its present, its motion, its chemistry, its path, but its past remains veiled, a soft story told only in hints, and there's another gentle unknown. How long has it been drifting? Interstellar space is vast. The distances between stars are so great that even at tens of kilometers per second, travel takes a long, long time. 3i Atlas may have wandered for hundreds of millions of years before coming anywhere near our solar system. During that time, it would have passed through the galactic disk. It would have crossed the arms of the Milky Way, feeling the slow pulse of starlight and dust. It may have felt the occasional tug of gravity, but mostly it would have been quiet, cold, waiting. Not waiting with intent, just existing, just continuing. And now, here it is, warming softly as it nears our sun, releasing molecules that haven't tasted heat in eons, whispering stories from a place we'll never visit. There's something deeply humbling in that. Because we often think of comets as parts of our solar system, familiar, predictable. But this one, this visitor, comes from elsewhere, and yet, in behaviour, it's not so different. It shines, it exhales, it drifts. That similarity is part of the wonder. It means the processes that formed it, whatever star it came from, weren't entirely alien. They followed some of the same rules, the same gravity, the same chemistry. Perhaps then, the galaxy is not as fragmented as it seems. Perhaps systems like ours are common. Perhaps planets form in many places. Perhaps the materials for life, ice, carbon, nitrogen, exist far beyond our little corner of space. 3i Atlas carries no message, but it offers that hope. A hope built not on faith, but on pattern, on repetition, on the gentle consistency of cosmic processes. It came from far away, but it feels somehow familiar. And as we watch it pass, we're reminded that even in the vastness of space there are echoes, and sometimes they find their way here. As the story of 3i Atlas unfolds, it brings with it not just observation, but interpretation. And in that interpretation, there is room for speculation, most of it grounded, calm, built on data and models, but some a little more imaginative. Soon after the comet's trajectory was confirmed to be interstellar, whispers began, both among professionals and in the public sphere. Could it be more than it seems? Could it, perhaps, be artificial? It's not a new idea. We've heard echoes of it before, most notably with Oumuamua, that object's strange acceleration, lack of a visible coma, an unusual shape led some to wonder if it might be a relic of intelligent design, a probe perhaps, or a kind of light sail drifting through space. With 3 Atlas, the similarities are fewer. It behaves more like a typical comet. It outgasses, it forms a tail, its chemistry aligns with what we expect. But its size, its brightness, and its precise path have still given a few thinkers pause. Some wonder, what if it's not just a comet? What if it's carrying something? Not passengers or machines necessarily, but data or design. What if it's a delivery from another system, not in intent, but in consequence? These musings live more in the realm of possibility than probability. They're not the dominant view among scientists. Most astronomers agree that 3i Atlas is natural, formed like other comets, shaped by gravity and ice and time. There's no hard evidence for anything else. But still, we allow ourselves to wonder, gently, quietly. Because sometimes, questions are as valuable as answers, and even if this object is nothing more than a very old, very cold fragment of another system, that alone is extraordinary. It tells us that the boundaries between star systems are permeable. That material moves. That nothing in the galaxy is entirely isolated. And if we entertain more speculative ideas, we do so not out of fear, but curiosity. The kind of curiosity that leads us to build telescopes, to launch missions, to watch the sky. Some researchers, including a few high-profile scientists, have suggested that we should treat all interstellar objects as potential techno-signatures, not because we expect them to be artificial, but because we shouldn't assume they're not. It's a cautious kind of openness, a willingness to test even the unlikely, just in case. That's how discovery often happens. With 3-Eye Atlas, the idea has even reached political ears. A few voices in government have echoed the possibility, suggesting we monitor the object closely just to be sure. Perhaps even send a mission, if we can act quickly enough. But in truth, most efforts remain focused on the science, on the motion, the composition, the glow of dust in the dark. And yet, something about these visitors touches us differently than ordinary comets, because they don't belong here, and because they arrived without warning, without invitation, without explanation. That too is part of the awe. In a universe governed by physics, sometimes strangeness alone is enough to make us pause, and yet, as we sit with these thoughts, we return to something steady: the data. So far, every observation of 3-Eye Atlas fits with what we know about natural comets. The tail grows in proportion to solar heating. The coma's expansion matches models. The chemical signature, though slightly rich in carbon monoxide, remains within expectations. Its speed, while high, is not inexplicable. Its orbit, while steep, is consistent with an unbound trajectory. Its brightness, while notable, fits with its estimated size. So we breathe, and we watch. And we let the more extraordinary ideas sit quietly at the edge of our minds, acknowledged but not chased. Because sometimes mystery is enough. It reminds us to remain open, to remain alert, but also to remain grounded, to let the universe reveal itself in its own time and in its own way. If we ever do encounter something truly artificial, something not shaped by gravity or dust or ice, it will be unmistakable. But until then, we listen, we measure, we observe. And with 3-Eye Atlas, what we observe is a comet, ancient, foreign, beautiful, and more than anything, real. As it continues its inward glide, 3-Eye Atlas draws close to Mars, a quiet encounter that marks one of its closest brushes with a planet on its way past the Sun. The date astronomers have marked is October 3rd, 2025. On that day, the comet will pass within about 0.19 astronomical units of Mars, just under 30 million kilometres. Not a near miss, but close enough for a clear view. And for a few brief nights, the red planet and this interstellar traveller will share the same stretch of sky. It's not the kind of event that makes headlines. There's no danger, no gravitational upheaval. But for scientists and space watchers, this moment matters. It's a rare alignment of motion and time, a visitor from beyond our solar system brushing past one of our oldest planetary neighbours. Mars itself, quiet and cold, will likely notice nothing. Its thin atmosphere won't respond to the passing dust. No meteor storms, no atmospheric streaks. But orbiting high above the Martian surface are spacecraft, NASA's MAVEN, ESA's Trace Gas Orbiter, and others still operational. And while most of them weren't designed to observe comets, they may still catch a glimpse. More exciting are the instruments back here on Earth, and those orbiting Earth. Telescopes already tracking 3-Eye Atlas will be watching closely during this time, because as the comet nears Mars, its distance from us will change too, offering a new geometry for observation, a different angle, a different phase of its tail, subtle shifts in reflected light that reveal structure, shape, and possibly surface texture. This flyby is especially useful for understanding the coma's behaviour. As the comet nears perihelion, its closest point to the Sun, it becomes more active, more gas escapes, more dust is flung outward. By catching it as it passes Mars, astronomers can monitor this increase in activity almost in real time. There's a soft kind of choreography to all of it. The alignment of orbits, the gentle physics of motion, nothing collides, nothing halts. Everything flows forward in a pattern shaped by gravity and time. And yet, even in this slow ballet, there's opportunity. Some teams hope to measure how the solar wind shapes the comet's tail during this phase. Others are watching for shifts in the coma's density, hoping to model how deeply the sun's warmth is penetrating into the nucleus. And still others are simply taking images, building a frame-by-frame record of how 3i Atlas changes as it journeys closer to our star. There's also something quietly beautiful about the image itself. Mars, with its rust-red surface, orbiting steadily around the sun, and this icy visitor from another system passing nearby. Two very different worlds. One old and weathered, its surface shaped by dust storms and dry winds. The other pristine and untouched, its surface never kissed by atmosphere, never shaped by erosion. Just ice, just time. And though they'll never meet, never interact, their shared moment in the same quadrant of the sky is a kind of cosmic nod, a reminder that motion connects us all. From Earth, of course, we won't see both together. The alignment is more about orbits than visual proximity, but for those tracking the data, it's a rare and useful benchmark. It helps refine the comet's trajectory. It helps test gravitational models. It gives observers a sense of timing that they can use as 3i Atlas continues its flight. Because not long after this encounter, it will move toward its closest point to the sun. The Mars flyby is a prelude, a chance to see the comet under moderate solar heating before the full warmth of perihelion reaches it. It's a moment to take stock, to measure outgassing rates, brightness changes, tail development, so that when it nears the sun a few weeks later, we'll have something to compare it to. Will it brighten rapidly? Will the tail split or twist? Will new jets of gas erupt from the surface? These are the quiet questions astronomers will be watching for. And Mars, silent and still, will be there in the frame, a planet shaped by ancient forces, now watching a traveller from another system drift by. And for a moment, we're reminded of scale. Not in kilometres or velocity, but in time. Because while this encounter lasts only a blink in cosmic terms, the object passing Mars has been on its journey for eons. And the planet it passes, a world we've only begun to explore, has been orbiting the sun in near solitude, waiting. Now, for just a few days, they share space, not as destination and visitor, but as two participants in the ongoing rhythm of the galaxy. And as we drift with them, tracing their slow alignment in our minds, we find something gently profound. There's meaning even in moments of passing. After Mars, 3i Atlas continues its slow descent toward the heart of our solar system. Its trajectory curves gently inward, following the subtle guidance of gravity, until it reaches its closest approach to the Sun, its perihelion, on October 29th, 2025. At that point, it will be just 1.36 astronomical units from the Sun, not unusually close, roughly the distance between Mars and the Sun, but close enough for the solar warmth to fully awaken the surface. This is the turning point in the comet's journey. Not in its path, because it will continue outward after this moment, but in its behaviour. It is here, in this narrow window of days and light, that the outgassing reaches its peak. The coma grows fuller, the tail stretches longer, the chemistry reveals its richest layers. We often imagine perihelion as a dramatic event, a flare of heat, a burst of activity. But in truth, it's often a quiet blooming. The sun's energy penetrates deeper into the nucleus, warming ices that had remained dormant. Molecules trapped in pockets for perhaps 1 billion years finally escape, streaming into space in arcs shaped by the comet's rotation. This is the moment astronomers have been waiting for. Every telescope trained on 3i Atlas will be watching closely, because perihelion offers a kind of window into the comet's core. Not literally, of course, we'll never see the inside, But by measuring how the surface responds, we begin to understand what lies beneath. If there are layers, strata of ice and dust from different phases of its formation, they may sublimate at different rates. That will appear as changes in brightness. If certain gases appear now that weren't seen before, carbon monoxide, ammonia, even faint traces of more complex organics, that gives us insight into the temperature gradient below the surface. And if jets emerge, collimated outflows of gas and dust, they can tell us about the internal structure, cracks, cavities, subsurface ice reservoirs. Each one whispers a different chapter of the comet's long history. From Earth, observers will track these changes through light curves, spectra and images. They'll compare observations taken before perihelion to those taken after. They'll look for asymmetries. Does the coma shift shape? Does the tail curve differently? Does the rotation speed change, perhaps slightly, due to the uneven thrust of escaping gases? There's also a philosophical beauty in perihelion. It marks the moment when this object from the cold interstellar dark comes closest to our star, to our light, to the central warmth that sustains life here on Earth. And then, just as gently, it begins to retreat. That shift from inbound to outbound is not sudden, but it is certain. From that moment on, 3i Atlas is on its way out. The sun will still shine on it, yes, but from a greater distance. The heating will slow, the activity will fade, the coma will thin, the tail will begin to fray. Some comets fragment near perihelion, the heat becomes too much, pressure builds, cracks widen, and the object breaks apart into multiple pieces, each one following a slightly different path. This is especially common with loosely bound comets or those making their first approach to the Sun, but 3 Atlas so far shows no signs of such weakness. Its outgassing has been steady, its structure seems stable, and its approach isn't especially close, far enough that catastrophic breakup seems unlikely. Still, astronomers will be watching, not with worry, but with curiosity, because even a small crack, even a gentle fragmentation can reveal something we couldn't otherwise know. The layering of the interior, the cohesion of materials, the age of different deposits. There's also a question of brightness. Some comets reach their peak visual brightness at perihelion, others brighten slightly after, as their activity increases and the coma fully expands. For 3i Atlas, models suggest the latter, that its most visible phase may come days or even weeks after closest approach. This means the best views may still lie ahead. Skywatchers with large telescopes may capture more detailed images. Spectrometers may detect molecules previously hidden, and the slowly lengthening tail may begin to interact with the solar wind in new, beautiful ways, twisting, rippling, shimmering. We may even, briefly, be able to see it with small instruments, binoculars perhaps, or long exposure cameras. Not a grand light show, not a comet for crowds, but a faint signature, a gentle trail of interstellar stardust caught in the sun's light for a passing moment, and then it moves on. The moment of perihelion will pass without a sound. No flash, no celestial note, just a line on a chart, a point on a path. But in that line is something rare, the closest embrace between our star and a body born far beyond its warmth. And for a few short days that embrace will glow. After perihelion, 3i Atlas begins its long glide outward, away from the sun, away from the inner solar system, away from us. But before it slips entirely into darkness again, it draws close to Earth. Not closely in terms of threat or impact, but closely enough for one last good look. That moment will come around December 19th, 2025. On that day, the comet will be roughly 1.8 astronomical units from Earth, about 270 million kilometers, still very distant, still beyond the orbit of Mars, but positioned in a way that gives observers here on Earth one of their clearest views. Not brightest, necessarily, but geometrically favourable. The angle between the comet, Earth, and the Sun offers a chance to watch the tail stretch in profile, to trace the fading coma, to listen one more time to the chemistry of what remains. For astronomers, this is a kind of closing act, an encore performance before the curtain falls. Because by this point, Three-Eye Atlas will have passed its peak brightness. The sun's influence will be diminishing, the surface will be cooling, the outgassing will slow, but the view, especially with modern instruments, will still be rich. Ground-based telescopes will watch the tail fade. The most sensitive spectrographs will continue scanning for molecules, tracking how the composition changes as different ices stop sublimating. They'll be looking for heavier compounds, things that only emerge late after the lighter gases have dispersed. And because we now know the object's orbit with greater precision, many smaller observatories, university programs, amateur networks, robotic telescopes will participate. It becomes a shared moment, a kind of communal gaze. There's something meaningful in that. We often think of astronomy as remote, detached, lonely. But in moments like this, it becomes collective. Across continents, across time zones, people point their lenses toward a fading light and know they're watching the same thing, something from beyond. There's also a different kind of observation happening at this stage, not just scientific, but symbolic. Because this is when we say goodbye. When Oumuamua passed Earth, it did so quickly, already outbound, already fading. Borisov came and went with more notice, but still passed without lingering. Three-Eye Atlas, in its slow and steady path, offers us a longer farewell, a few extra weeks, a more gradual turn toward the dark, and we can use that time. We can measure polarization, how light scatters off the dust grains. We can study the comet's structure using radar, though it's quite distant for strong signals. We can test how the solar wind shapes its now thinning tail, and perhaps most importantly, we can continue to refine its trajectory, not just where it's going, but where it came from. Because even now, even in the final phase of its visit, Three-Eye Atlas still carries secrets. Its outbound path contains traces of all the forces that shaped it, gravitational nudges from the Sun, from Jupiter, from Mars. Every bend tells us something. Every deviation, however slight, sharpens our understanding. And with that understanding, we might someday trace its path backward, not just into interstellar space, but into the past. Astronomers may never be able to name its origin star, but perhaps they'll narrow it down. Perhaps they'll identify a cluster or a stream. Perhaps one day they'll find that this small comet came from a system whose light still reaches us, dim and distant, but real. Until then, though, we observe. From our position on Earth, orbiting a modest star in a quiet arm of the galaxy, we look outward, and we catch, for a little while longer, the soft shimmer of a visitor that reminds us we're not alone in this vastness. And while there's no danger, no impact, no interaction, there's a kind of intimacy in the nearness, in knowing that this object, formed in a different corner of the cosmos, is now passing through ours, responding to our sun, whispering through our space. It won't return. The orbit is open. The velocity is high. This is not a member of our solar family. It never was. But for a brief season, it shares our sky, and even as it fades, we follow. As Three-Eye Atlas begins its slow departure, it doesn't exit untouched. The solar system, vast as it may seem, is not an empty hallway. It's a space full of motion, of planets, fields of dust, faint magnetic boundaries, and above all, gravity. The next significant encounter on its journey outward will come in March 2026, when it passes relatively near Jupiter. Not close enough to be captured, not close enough to be redirected, but close enough for the gas giant's immense gravity to tug slightly at its path, a soft bend, a gentle rephrasing of the arc. Jupiter, often called the solar system's gatekeeper, has been shaping the destinies of comets and asteroids for billions of years. Its vast mass exerts influence across astronomical units, subtly changing the course of objects that pass near. For some, that pull becomes a capture, a looping orbit, a chance to become part of the solar system's long-term architecture. But for 3i Atlas, the velocity is too great. Its hyperbolic trajectory is already assured. Jupiter will not keep it, but it will nudge it, just a bit. Enough to shift the angle at which it exits, enough to slightly alter the shape of the path it takes into interstellar space. That subtle redirection may seem small, but it matters. Astronomers will study that bend carefully. It helps refine gravitational models. It offers a rare opportunity to observe how a fast-moving interstellar object reacts to a planetary mass under known conditions. And it gives us one final observational milestone before the comet fades beyond even our most powerful instruments. There's also something symbolic about Jupiter's role here. This is the planet that protects us in a way, sweeping up potential impactors, diverting debris, influencing the structure of the asteroid belt. It's a silent guardian of sorts. And here it is again, shaping the path of a visitor we'll never meet, never touch, never understand in full. Jupiter won't be the last influence 3i Atlas feels. As it departs the solar system, it will gradually enter the realm of interstellar gravity once more. The sun's pull will weaken, replaced by the soft, slow influence of the galactic tide. Its path will eventually become part of a larger orbit, an arc around the centre of the Milky Way. Not in the sense of planetary motion, but in the quiet drift of matter between stars. It will take millions of years to complete even a fraction of that arc, and we'll never see it again. Still, we can model it. We can estimate its outbound velocity. We can trace its course as it leaves the sun's domain, and we can imagine the space it will enter. Cold, dark, almost entirely empty, but not quite, because out there, in the interstellar medium, lies a whisper of hydrogen, a scattering of dust grains, the occasional charged particle, and perhaps, just perhaps, other objects like 3i Atlas wandering quietly through the dark. Maybe it will pass another solar system someday, maybe it won't. Its journey will be long and silent either way, but what matters now is that we saw it, that for a brief time it was part of our story, that it passed through the gravity of our star, felt the warmth of our light, and left a trail of dust and data behind. There's also a subtle emotional rhythm to this departure. It's not just the loss of an object we've studied, it's the closing of a rare opportunity. These interstellar visitors are few. Detecting one, tracking it, learning from it. All of that depends on timing, alignment, readiness. We don't control their arrival. We don't summon them. We only notice when they happen to pass close enough for our instruments to catch. And when they leave, they take with them the things we didn't yet learn, the questions we didn't yet answer, the mysteries that must wait for the next one. Still, we don't call it a loss. In astronomy, every goodbye is also a record, a path traced, a light curve captured, a moment that becomes part of the long collective memory of our exploration. We'll remember how 3i Atlas behaved as it neared the sun, how it glowed, how it released its gases, how it passed Mars, Earth, and Jupiter without a sound. We'll remember the quiet surprise of its discovery, the shared attention it drew, the instruments we turned toward it, and above all, we'll remember that it came from somewhere else, that it wasn't born here, that it wasn't shaped by our star, that it carried the signature of another place, another time, another system. That knowledge will stay with us long after the comet is gone, because even as it slips into the dark, the imprint of its presence remains. So what is the worst-case scenario? The question rests quietly in the background of every conversation about 3i Atlas. It isn't shouted, it isn't urgent, but it's there. Half curiosity, half caution. When something arrives from beyond, uninvited and unbound, it's natural to wonder, could it harm us? And the short answer is no, not this time. 3. Atlas will not strike Earth. Its trajectory has been calculated, checked and refined many times over. It passes at a comfortable distance. The orbit is steep but well behaved. No last-minute turns, no uncertain entries, no possibility of impact. But the question still matters, not because of this object, but because of what it represents. It asks us to look forward, to imagine a future where an interstellar object does come closer. Not a softer visitor like this one, but something larger, or faster, or just less predictable. The worst-case scenario in that context isn't fear, it's unpreparedness. We're good at tracking things inside our solar system, asteroids, comets, space debris. We've mapped tens of thousands of near-Earth objects and built systems to monitor them. But interstellar visitors are different. They come from outside, they move faster, their arrival is sudden. Their paths are steeper, and we've only seen 3. Each one has been a surprise. Oumuamua wasn't recognised until it was already leaving. Borisov gave us a little more time. 3 Atlas was spotted earlier still, but in each case the detection happened after the object had entered the solar system. That's the concern. Not that any one comet will hit us, but that we may not see it coming, because interstellar objects don't orbit our sun, they don't loop back, they don't give us multiple passes to study, they arrive quickly and they leave just as fast. In a true worst-case scenario, an object much larger than 3I Atlas could enter on a steep trajectory and go undetected until it was already very close. Even without striking Earth, the dust it carries could affect satellites. Its tail could interfere with the orbits. A closer pass could create auroras, light scattering, even minor atmospheric effects. And if, just if, something were large enough, fast enough, and on a direct collision course, we'd have little time to respond. Days, maybe weeks, not years. That's why astronomers care so deeply about detection. Because while this moment is peaceful, it's also instructive. Each object we track improves our understanding of what's possible. Each trajectory helps refine our models. Each comet shows us how to spot the next one earlier. There are plans to improve that readiness. Missions like the NEO Surveyor will help detect objects approaching from the direction of the Sun, currently a blind spot for ground-based observatories. Space-based infrared instruments could identify interstellar visitors even before they become active. Automated alert systems could speed up global observation once a candidate is found. We're getting better, and beyond detection, there are even conceptual missions being drafted to intercept these objects. The idea is simple. Launch a spacecraft fast enough to catch up, study the object close up, maybe even land, maybe even sample. Difficult, yes, but not impossible. Because while Oumuamua moved too fast and Borisov came too quickly, future missions could be waiting, could be ready, could be aimed like arrows the moment the path is clear, but none of this is rooted in panic. Rather, it's the calm logic of astronomy. See clearly, prepare wisely, respond gently. The worst-case scenario isn't just an impact, it's a failure to observe, a failure to wonder. A failure to invest in the quiet, watchful science that keeps us informed. And so, 3I Atlas becomes more than a visitor. It becomes a rehearsal, a reminder, a soft prompt that asks us, are we paying attention? So far the answer is yes, but it must stay yes, because while this interstellar comet brings no danger, it brings something just as important, a chance to practice, a chance to notice, a chance to be ready before we must. And that readiness, like the object itself, is a gift from the stars. The further 3I Atlas drifts from our sun, the more it begins to slip into silence again. Its tail softens, its coma thins, its shimmer fades into the starfield. It leaves behind no trail we can see with the naked eye, no signpost in the sky. but in the data, layered, stacked, studied, it leaves a quiet richness. This is what comets do in the end. They come, they glow, and they go. But interstellar comets, they also reveal. Each one that passes through teaches us something not just about itself, but about the space between stars, the chemistry of other systems, the mechanics of planetary formation far away from here. The way material can survive unchanged for billions of years and still, even now, share its story. What 3i Atlas leaves us with, perhaps most of all, is a lesson in perspective. Because when something arrives from beyond, it stretches our sense of where here ends and there begins. It softens the border between solar and interstellar. It reminds us that the sky is not a dome, but a bridge. One where matter crosses, sometimes slowly, sometimes quietly, from one star's influence to another's. In that way, 3i Atlas becomes part of a much larger structure, the quiet, invisible weave of the cosmic web. That vast pattern of galaxies and gas, stars and filaments that links everything, our sun, our planets, our comets. They are threads in that structure. So is this visitor. Its path may seem random, but even randomness has rules. The object moves according to mass and momentum, curvature and drift. It follows laws we understand, and yet the result is motion that feels graceful, like choreography written in silence. We often talk about objects in space, asteroids, comets, planets, as if they're separate things. But they're also participants in a shared unfolding, the story of matter organizing itself, breaking apart, reforming, and moving on. And occasionally, just occasionally, one of those participants passes through our field of view. We rarely think about what the galaxy looks like in real time. We're used to seeing snapshots, photos of nebulae, diagrams of orbits, light curves frozen in charts. But the galaxy moves. Stars orbit the centre. Clouds of gas drift and collide, and objects like 3i Atlas glide silently between all of it. Perhaps it came from a planetary system that failed to form. Perhaps it was ejected early before any planets coalesced. Perhaps it passed near other stars before reaching us, nudged and turned, shaped by invisible hands. It's even possible, however faintly, that it has passed through another solar system since its ejection. In that scenario, we're not its first observer, just the first to notice. There's something deeply humbling in that. To think that this small comet, this quiet fragment of ancient ice and dust, has been moving through the galaxy for untold eons, and we, on this small planet, happen to spot it during its brief passage through sunlight. A gentle reminder that timing matters, that attention matters, that wonder matters. Because we didn't catch 3i Atlas by accident. We built instruments, we scanned the sky, we learned from the past. And we watched the dark until something moved. That act of patient watching is one of the quiet triumphs of science. No fanfare, no explosions, just light and time and focus. And when that light fades, as it now begins to do, we don't chase it. We record, we remember, we prepare for the next. 3i Atlas may be gone from sight within a year or two. It may never be seen again, but its presence will echo, in models, in databases, in the minds of those who turn their lenses toward it, night after night, waiting for a flicker of insight, and for the rest of us, those simply listening to its story. Following its arc in our imagination, it leaves behind a quieter kind of trace, not a trail in the sky, but a widening of the mind, a sense that even here, even now, the galaxy still sends messages, not in words, not in signals, but in motion, in matter, in slow, ancient fragments that pass through our lives and then continue on. As 3i Atlas fades into distance, into quiet, into the beyond, we don't lose it. We join it. if only briefly, in our thoughts, because everything that moves across the cosmic web leaves a ripple, and some ripples carry wonder. Earlier, we drifted past the idea that 3i Atlas carries fragments of its origin system, molecules shaped by a star we will never see, minerals condensed in a dust cloud older than our sun. But there's more than matter in its trail. There's also motion, and in that motion lies a different kind of signal, one that whispers not just where it came from, but what surrounds us silently all the time. We often think of signals in space as dramatic, radio bursts, pulsars ticking, the flash of a nova. But the universe also speaks in softer ways, in backgrounds, in barely detectable fields, in particles that pass through our bodies without pause or harm. And among those, gravitational waves and neutrinos are perhaps the quietest and most persistent of all. Though 3i Atlas doesn't produce these signals itself, its passage through the solar system reminds us that we too are passing through something vast and unseen, a field of waves and relics that began long before the first comet, before the first star, before even atoms were born. Consider the cosmic neutrino background, a sea of faint, ghost-like particles released just seconds after the Big Bang. They stream through the cosmos at nearly the speed of the light, barely interacting with anything, including us. They pass through planets, stars and comets like 3i Atlas without slowing, and yet they are there, billions passing through your body each second, unfelt, unstopped. The comet is no different. As it glides through space, it crosses this background, just as it crosses the cosmic microwave background, the afterglow of the universe's first light, just as it floats within the slow flexing of gravitational waves, tiny ripples in the fabric of space-time caused by distant cataclysms. We can't observe any of these with the naked eye, but our instruments can, carefully, quietly. And so, when we look at 3i Atlas, we're not just looking at a comet, we're looking at a point of interaction between an object and the invisible canvas it moves through, a place where ancient matter intersects with ancient light, where a visitor from another star brushes softly against the echoes of the beginning. Some might call this poetic, but it's also physical, real, measurable. The gravitational waves are faint, but they stretch every particle of space by an imperceptible amount. The comet feels them, not with pain, not with resistance, but with subtle shifts in its path, just as everything else does. And though we can't detect such shifts in this single object, we know the waves are there, stretching, softly, always. Similarly, the neutrinos that pass through 3i Atlas carry no image, no momentum, but they do carry information. They are relics of the first seconds, just as the comet is a relic of another system's formation. Both are messengers, both are travellers, both are evidence that the past still flows through the present. Then there's interstellar dust. More familiar perhaps, but just as quiet. The comet's motion through the solar system stirs it faintly. The particles it sheds may interact with this dust, altering the texture of the tail, leaving ripples we can just barely see. The sun's light pushes on that dust too. Radiation pressure and the solar wind reshape the soft edges of the coma. Even light, it turns out, leaves fingerprints, and all of this brings us back to one central realization. We are not only observers of cosmic signals, we are inside them. Our entire planet spins beneath a stream of neutrinos. Our telescopes float inside a bath of relic light. Our instruments stretch and relax with the passing of gravitational waves. The signals are everywhere, not just in what we detect, but in what we inhabit. In that sense, 3i Atlas is not a disruption, it's a participant, like us. Its orbit, its motion, its slow arc through our skies, it all happens within these ancient fields. It doesn't just reveal them, it reveals our place within them. Because when we see a comet like this, we don't just see ice and dust, we see alignment of timing, of motion, of presence. And in that alignment, something stirs. a quiet knowing that we are immersed in a cosmos that never stopped speaking, that still murmurs its beginning through light and particles, that still reveals its shape through ripples and motion. 3D Atlas won't carry these signals with it when it leaves, but its presence helps us remember they're always here, not loud, just persistent. As the light of 3i Atlas grows fainter and the comet recedes into deep space, we find ourselves lingering not just on the object itself, but on the meaning of its passage. What does it tell us? Not just about chemistry or gravity, but about our place in the great unfolding of the cosmos. To meet a traveller from another star is a rare privilege, but perhaps it's more than that. Perhaps it's a kind of invitation, a chance to ask gently what kind of galaxy we live in, a chance to wonder whether we are truly alone, not just as individuals or as a planet, but as a civilization. Because in every conversation about interstellar objects, the question arises, softly, carefully, about life. Not because 3i Atlas shows signs of it. It does not. There are no emissions, no engineered features, no markers of intention. It is ice and dust. That's all. But still, its presence opens the door. It reminds us that the material for life, water, carbon, organics, exists beyond our solar system, that the forces that built our planets are not unique, that ejections happen, that fragments travel. So what else travels? Might there be comets someday that carry more than molecules? Might there be worlds adrift, rogue planets with atmospheres and oceans warmed by interior heat? Might there be signals we haven't yet learned to hear, carried not by radio waves but by geometry, or chemistry, or light itself? It's a slow unfolding. Astronomers have long searched for signs of biosignatures, chemical markers in exoplanet atmospheres that hint at metabolism, respiration, cycles. We look for oxygen in excess, for methane coupled with carbon dioxide, for unusual balances that suggest something living beneath the haze. And yet, in the background of that search, 3i Atlas whispers a different kind of question. Not, is there life where I came from? We can't know that, but rather, am I part of a shared story? A story in which matter does not stay still. A story in which comets and dust and fragments of failed worlds drift from star to star, slowly seeding, slowly shaping, slowly connecting. Some scientists speculate that the earliest organic molecules on Earth may have come from such objects, from comets, asteroids, perhaps even interstellar debris that fell into our early oceans. It's called panspermia, the idea that life, or the chemistry that leads to it, may travel between systems. It's not a proven idea, but it's not impossible. And when we see an object like 3i Atlas with carbon-rich outgassing, with traces of cyanide and nickel, with a structure that has survived light years of drift, we begin to see the possibility. Not of life aboard, but of life enabled. Because this object has endured. It has protected its chemistry for longer than human civilization has existed. Perhaps longer than Earth itself. It carried that chemistry across the vastness of space and shared it with our sun. For a moment it became part of our system, and then it moved on. It may never come near another star, or it may drift into another system ages from now unnoticed. Or perhaps it will fall into another gravitational well, warm again, outgas again, and reveal its molecules to someone else. And that in itself is profound. Because whether or not life exists elsewhere, the potential for connection is everywhere. Comets like 3i Atlas are not signs of intelligence, but they are signs of motion, of shared material, of bridges between systems. And when we look into the sky and see one, we are reminded the galaxy is not a static place. It breathes, it circulates, it whispers. Even across millions of years, even across trillions of kilometers, something as small and silent as a comet can still carry meaning. We listen, we observe, and somewhere within that observation, we feel less alone. Not because the comet speaks, but because it reminds us that things travel, that stories don't always end where they begin, that in the quietest, coldest corners of space there is still motion and memory and meaning, and that maybe, just maybe, that's all life ever really needs. And now we come to the part of the journey where we must begin to let go. The Atlas, once bright enough to catch the attention of observatories around the world, now fades slowly beyond the reach of even our most sensitive lenses. Its path continues outward, slipping back into the deep, cold quiet from which it came. And yet, there is no final moment, no dramatic exit, just a gradual softening, like a voice trailing off in the distance, like a ripple expanding until it becomes part of the stillness again. We may never detect it again, but it is still there. It will always be there, somewhere beyond the light of our star, gliding into the galactic dark, leaving behind no dust, no signature, only knowledge, only memory. And in this fading, there is beauty. We often think of endings as something sharp, but in space endings are soft. A comet doesn't stop. It doesn't vanish. It simply continues until we are no longer able to follow, until the last photons scatter too faintly for us to gather, until the trail becomes wider than our questions. Still, it has changed us. We now know that such visitors exist, that the galaxy does not just send us light and radiation and signals, but objects, travellers, fragments of other places. Bodies that carry with them the quiet legacy of a star's formation, of planetary turbulence, of ancient scattering and deep time drift. And in its quiet way, 3i Atlas has reminded us that the cosmos is not composed of fixed things, but of moving relationships, everything in orbit, everything in motion, everything influencing everything else, however gently. Even a small ice-cored wanderer from another system, unseen for most of its existence, still matters. Because it touched our sunlight, because we noticed, because we will remember. Perhaps that is the heart of the story, not the trajectory or the chemical signatures or the eccentricity of its orbit, but the simple fact that we were here, paying attention when it passed through. That matters. It means something to notice the universe, to track it, to record its passing voices, even when those voices do not speak in language, even when they whisper in tailwinds and spectra and faint arcs of motion. We saw 3i Atlas. We shared the same sky. We listened as best we could, and now we send it back to the dark, not in farewell, but in gratitude for what it brought, for what it showed us, for the calm urgency it awakened in our science and the hush of awe it left in our thoughts. Let it go now. Let it drift. It has already given all it can, and all we can do, all we must do, is continue the work it quietly encouraged, of looking outward, with wonder sharpened by patience, because there will be others. One day, another object will glide in from the shadows, and we'll be ready to meet it. And now, with the journey complete, we let the last light fade. The glow of 3i Atlas, once traced through the night by quiet instruments and careful eyes, has long since thinned into memory. But its story remains, gently echoing in the folds of time and thought. We followed its path from beyond the stars to our corner of space, watched it stretch a tail in sunlight, and listened to the science it offered, softly, steadily, with no need for urgency. A fragment of another world, perhaps older than our own, shared a brief moment with us before slipping away once more. And now, as you breathe in and breathe out, you might picture it, still drifting, far from heat or light, crossing that vast and velvet dark, not seeking, not fleeing, simply continuing. We remain here, of course, wrapped in gravity and warmth, turning under our sky. But our sense of scale has shifted. Our perspective has widened. We carry now the quiet knowledge that even in a universe so vast, something as small as a comet can find its way to us and be seen. So breathe again. Feel the softness of your blanket, the hush of your room, the familiar rhythm of your heart, all the complexity of life, unfolding here under a sky that once welcomed a whisper from deep time. No need to hold on to the whole story. Let it drift. Let it settle behind your eyes like starlight, gentle, weightless, and far away. Sleep now, knowing that we are listening, watching, wondering. And when the next visitor arrives, wherever it may come from, we'll be here,